Welcome to the lecture on igneous rocks. Hopefully we'll get through this in 2 sessions, maybe even 1 if I can talk quickly. First, how is a rock different from a mineral? Real quickly, a mineral is one substance, the same molecule with the same atom over and over. A rock most often is made of minerals. There are exceptions, like rock salt is made of salt, halite, NaCl. Quartzite is primarily SiO2, quartz. But you get the idea. Rocks in general are not pure substances. They're mixtures of minerals. Your book starts going into the rock cycle, but we haven't even talked about rocks, so let's wait to talk about that until we're done with rocks. Because we're talking about hot stuff, I thought this might be good to throw in. The stuff we're talking about is not picante hot, we're talking caliente hot, stuff that's molten. If you remember, not that far underneath you, less than 100 miles, there is molten or plastic material. We never think about this. We think our Earth is solid. Not so. The magma underneath us isn't that far away. And on occasion, that magma escapes to the surface as lava, not quite the same as magma because gases are released and minerals are dropped out along the way, and creates the volcanoes. We can divide all this into intrusive and extrusive. Intrusive, like inside, internal, means anything inside the Earth. We've got radioactive decay, we've got pressure, we've got residual heat, we've got sedimentation going on. All these create heat, which then melts the mantle, which then becomes less dense, and it rises sometimes to the surface, creating extrusive igneous rocks, which we know of as either quiet volcanoes, like this eruption in Kilauea, Hawaii, or this artist conception of Pompeii, or Vesuvius erupting over Pompeii. And I want to say that was 79 AD, but I'm not exactly sure. I was just a kid then. Let's talk about rocks that form under the ground first. We don't have any photos of those happening because, well, it'd be kind of hard to take pictures. But extra credit for you if you want to do that. Here are 3 sample rocks that form underground. You'll notice they have something all in common. They all have crystals. Why? Because when you're underground, you cool very slowly. In some cases, well over 1 million years it takes to cool down. That allows the molecules and atoms in you to get organized with all their buddies and create crystals. A slowly cooling material has time to create crystals. So if you see a rock with crystals, you know it didn't form on the surface. It occurred down here, somewhere under the surface. Unless it was done by evaporation. There's an exception. Now, we can also classify rocks according to their silica content. If they have a lot of quartz and feldspar, they tend to be light colored. If they have less quartz and feldspar, they tend to be dark colored. These are said to be felsic, like feldspar and silica, Fel, and Si, felsic. These are mafic because of iron, Fe, and magnesium, Ma, mafic. Those words are not so big. Just know that we have dark ones and light ones, and they're different chemically. They form from different lavas, by the way, or different magmas. This magma tends to be really thick. It has, well, we'll go into that later. Hang on. Again, less silica, more silica, silicon dioxide. The names of these are gabbro, diorite, and granite. Now, those of you who've gotten kitchen countertops made out of a stone, everybody in the kitchen countertop world calls everything granite. If it's a rock, they call it granite. It really isn't, but that doesn't bother them. Just bite your tongue and go, you're so right. Now, there is an exception to this standard thing. There's something called pegmatite. Pegmatite has extra large crystals, which usually indicates it cooled way down underneath even these guys. Very slow cooling. In the cases of some pegmatite pictures I've seen, they're crystals well over 2 meters long. Kind of crazy. That takes a long time to form. Once again, here are granite countertops. Oh, that's so nice. And depending on the materials in the granite, there are different names for it. For example, this is a felsite because it has lots of feldspar. You don't need to know that. Just know that it has big crystals, therefore it cooled slowly, therefore it cooled underground. This is where we use our granite mostly. Kind of sad. We take this beautiful rock that formed underneath the earth It has been pushed up to the surface like along the freeway at 16th Street and the 101. All that granite you're driving through goes into mines where it gets crushed up, and then we put it in our yards. Kind of crazy. I believe some of this granite is somewhere between 1.3 and 1.6 billion years old. In Egypt, it's just kind of crazy. These folks, a long time ago, figured out how to work with granite, polish it down smoothly, and they made all kinds of temples and obelisks out of various intrusive igneous rocks. Again, really large crystals, underground, and back east, at least, we have a lot of buildings made out of granite. Out west, we have more sandstone, so we do that kind of thing. So putting this all together, we've got gabbro, diorite, and granite for intrusive igneous rocks. Extrusive igneous rocks, well, here's one kind. It's called basalt. If you take gabbro and instead of cooling it down slowly, cool it down really quickly, you get this. How do you cool it down quickly? Well, you burp it up to the surface and have it cool quickly. Sometimes it has holes in it, so basalt with holes in it is called vesicular basalt. If it has a lot of holes in it, it's like a scoria, and you will see scoria all around Flagstaff. The old Coconino High School track wasn't made of this nice surface, it was made of pieces of scoria, which was really bad. When you fell on it, ouch. And that happened every track meet. So basalt is your less silica extrusive rock. We probably need to throw in here, if basalt has a lot of olivine in it, it's called peridotite, and this is just beautiful. If you're ever over in Hawaii and you see these green fibers next to the basalt, it is these little olivine crystals, and they've been stretched by the wind. Now, basalt often becomes oxidized, just like a desert varnish, and the Hohokam Indians out here by Mary's Knoll, north of the 101, left these markings in there. And again, here's olivine forming peridotite on basalt. Basalt, when it cools, does this really weird thing. It forms hexagonal columns or six-sided columns like stop signs, six-sided. Here's an example of what's happened, an old volcanic neck where the basalt was rising to the surface. Imagine the surface of the earth somewhere up here. This is down in the volcanic neck. This stuff cooled, and it shaves off in hexagonal columns. If you've seen the old movie Close Encounters of the Third Kind, this was featured in there. A medium-colored extrusive igneous rock is called andesite. It's essentially diorite, but burped up to the surface. It looks like it has big crystals, kind of, but it also has air holes in it. So if you see a rock with air holes in it, you know it's an extrusive igneous rock. You don't get air holes underneath. Think about it this way. You ever release the cap of a soda pop bottle and you see the bubbles escaping? The same thing happens here. When this stuff comes up to the surface of the earth, the pressure is released and the dissolved gases start expanding, frothing up the lava. It doesn't happen in magma. And the light-colored equivalent, extrusive equivalent of granite is rhyolite. So, gabbro, diorite, granite, basalt, andesite, rhyolite. How does rhyolite form? Rhyolite is really viscous. It doesn't flow really well. Imagine putting honey into the refrigerator and then trying to pour it. Taking it out first, of course, and then trying to pour it. That's like rhyolite. It's very thick. So when pressure builds up behind rhyolite trying to come out of the earth, it just explodes and spreads ash all over the place. In the case of Arizona, this has happened in the Superstitions, and down here in the Chiricahuas, this is left behind by layers of rhyolite that have been eroded away. This is in southeastern Arizona, not far from Kartchner Caverns. One more extrusive igneous rock. This. Obsidian. Some of you may know it as Apache Tears. The old story is taking the Apaches and walking them to Fort, I believe, Sumner in New Mexico, and along the way, leaving their homelands, the people cried as they were forced by the military to do this, and they cried tears. Good story, but these tears were there long before that. This is simply volcanic glass, and it looks dark, so you'd be tempted to classify it with the less silica things over here. But it really is almost pure quartz with a little bit of coloring in it. What? Well, think of Kool-Aid. Kool-Aid is mostly just sugar and water with a little bit of flavoring in it. When you stick that food coloring into Kool-Aid, it makes it dark, but it's really just water. Obsidian is kind of the same thing. If you chunk away a thin piece of it, this is what it's like in most cases. On other cases, you'll have this really opaque snowflake obsidian or colored obsidian. And here's snowflake obsidian. And over here to the east of Phoenix, near Globe, is the old Apache Tier mine. You used to be able to pay a few dollars and go over there and mine. They'd give you a bucket. It's closed down now, but I've taken my students over there. Here's something you can dig up, and here's what it looks like. It's about to collapse, so I think there are signs up there telling you, hey, it's about to collapse. Be careful. If we put all those rocks into one diagram, well, we left out peridotite and pegmatite, but that's okay. We get this. Extrusive rocks include basalt, andesite, and rhyolite obsidian. Intrusive rocks include gabbro, diorite, and granite. The ones on this end tend to be runny. They have little silica, so they're not quite as thick or viscous, and they're dark colored. Ones on this end tend to be very viscous. They make thick or explosive eruptions once they come to the surface. This is a nice little data table. You don't see any books make this, and I don't know why. One weird thing about, I didn't tell you about one other rock. Pumice goes in here. It not only is light in color, but it's light in that it has so many air holes in it, it floats. Nah, really? Yeah. Here is Vava'u down by Tonga in the South Pacific, not far from where I used to live in Samoa. Here is a new island, and the new island is releasing pumice as one of its rocks. The pumice is floating off. That's latte, not light. And being protected by this island and making a little pumice raft. Pumice occurred in some volcanoes, and scoria, by the way, in northern Arizona near Sunset Crater. And when the Glen Canyon Dam was completed in 1963 or 1964, it was made of concrete and a lot of pumice. You don't want to use the sandstone because sandstone is porous. So they used the pumice and the scoria from volcanoes northeast of Flagstaff. There also is a rock called tuff. When rhyolite explodes and sends all kinds of stuff out, when it becomes welded together, it is called a tuff, T-U-F-F. You can see this again in southeastern Arizona or in this old 1950s looking postcard of Los Alamos, New Mexico. All the mesas on which Los Alamos, our national laboratory where they developed the atomic bomb, are built, a tuff. Lots of pumice in it. Here is a biker on the tuff, and it can be fairly soft, so the old, not good. The old Jeep trails actually wore down into the pumice, tuff, rhyolite type rock, and you can still hike on those today. Now, magma versus lava. Magma is under the ground. Lava on top of the ground. Aren't they the same? Not really, because on the way, magma loses some of its minerals. As it comes toward the surface, it cools. It also gives off all kinds of gases. Here's magma. As it comes to the surface, I wish we could tilt this up this way, it loses minerals. So what we get on the surface isn't the same as what's underneath. We already talked about felsic versus mafic. I'm going to pause here, and we'll pick it up on the other side.